Hello everybody, and welcome to our second video on the fundamental theorem of calculus. So, oddly enough, despite the fact that this is the second part of our two-video series, this is the part where we're going to focus more on part one of the statement of the fundamental theorem of calculus. So we're going to just recall part one for now. Suppose f is continuous on the interval from a to b, then if cap a of x equals the integral from a to x of f of t dt, then a prime of x equals f of x. So, in other words, if you have a net area function or an accumulation function that starts at a and accumulates the values of the function ending at x, the rate of change of that accumulation is the little function f of x. So, what we're going to do is try to take a look at this graphically and see what this means. So what we have here, f is the function that's graphed here. But what we're going to evaluate is this function h of x, which is the integral from 0 to x of f of t dt. Okay, first we're going to start by evaluating h of x for x equal to 0, 1, 2, 3, 4, and 5. So for part A here, let's start with h of 0. Well, that's the integral from 0 to 0 of the function. And it should be clear that if you're taking an integral from 0 to 0, right, you're not covering any width. And if your width is 0, your area is 0. So this integral is 0. Okay, how about b? Or not b, h of 1, I should say. We're still in part A. h of 1. Well, that's the integral from 0 to 1 of f of t dt. So we're going to zoom in just a little bit here. So the integral from 0 to 1, that's this. That should be pretty straightforward. You've got a square here, a 1 by 1 square. And you've got a half of a 1 by 1 square, that triangle there. So that's 1 1/2 or 3 halves, right? But of course, that's the area. The value of the integral is actually the negative of that because this function is below the x-axis here. So here we get negative 3 halves. Now we'll take a look at h of 2. So that's the integral from 0 to 2 of f of t dt. And so now we look a little bit further. We look at this part as well. And the area here is 1/2. So we got 3 halves plus 1/2. That's 2 total. But again, it's negative. It's under the curve. That's negative 2. Okay, now let's take a look at h of 3. The integral from 0 to 3 of f of t dt. So here, we'll switch colors to green. So here, we've got the area between the curve and the x-axis. It's just 1/2, and this is positive. Now, here's the thing though. So far, we've already accumulated negative 2. And so we're taking that negative 2 and adding a positive 1/2. So this is actually negative 3 halves altogether. Okay, how about h of 4? It's the integral from 0 to 4 of f of t dt. So let's take a look here. I've got this area of this little square, that's just 1, and then we've got this triangle, and this triangle has width 1, height 2, and width 1, height 2. So 1/2 times base times height gives me an area of 1 altogether. So when I take the square and this triangle here, the area is 2. So our positive portion is 2 1/2. So 2 1/2, that's 5 halves. So we get negative 2, the negative portion, plus 5 halves for the positive portion so far. So that's a positive 1/2. Now we'll take a look at h of 5. And now we accumulate another 3 units under the curve. So altogether, we've got -2 from our negative portion, and then we've got 5.5 here. So 5.5, that's 11 halves. So -2 plus 11 halves is 7 halves. And finally, we're going to, for part B, we're just going to estimate h of 6 because the last part of this graph is not exact. So let's take a look. Well, we've got 1 down here, and so I'm just gonna kind of carve some pieces out. This square almost looks like a whole square. Maybe if I tossed this portion into here, that'd be 2. And then I've got like maybe another third, right? So I'm gonna say that this is approximately 2 1/3, which would be 7/3. Okay, so let's put all of that together. What do we have so far? Our negative portion of the graph, that's -2. The previous positive portion up to here was 11 halves. And then what's left in this portion is 7/3. And so let's go ahead and find a common denominator, which would be 6. This would be -12/6 plus 33 over 6. Plus 14 over 6. That's going to be, let's see, 47 minus 12. That would be 35 over 6. And again, I should specify that this integral is just being approximated here since we had a function that wasn't just a bunch of straight lines anymore. Okay, so now we've got our values for h at these different points. So we're going to go ahead and take a look at where does h of x have a maximum value and where does it have a minimum value. So for maximum value, it has maximum value when it stops accumulating positive values here, right? So here it's all negative. It starts adding positive portions, and it's going to be its largest value at the end. So h of 6 is the absolute maximum on the interval from 0 to 6 that we're dealing with. And for minimum, well, its minimum value is here at 2 when it's accumulated as much negative area as it's going to get, and before it starts adding positive value. So h of 2 is the absolute minimum. And then finally, part D says sketch a rough graph of h of x. Well, our largest value for h of x is this 35 over 6, which is pretty close to 6. So our graph for h needs to go from -2, which is the smallest value, up to a +6. And then we'll just plot the points. H of 0 was 0. H of 1 was -3 halves. Yeah, -3 halves. H of 2 was -2. H of 3 is -3 halves again. H of 4 is 1/2. H of 5 is 7 halves. That's 3.5. Right about there. And H of 6 is close to 6. So our graph looks roughly like this. Okay. Well, that's it for this one. Let's go ahead and move on to another problem. So now we're going to start using part 1 of the fundamental theorem of calculus to find the derivative of these accumulation functions. So here, what do we got? We have e to the sine of t dt. But what do I know? I know that if a of x equals the integral from a to x of f of t dt, a prime of x equals little f of x. Well, in this case, this is a to x. This is a function of t, dt. So my derivative, g prime of x here, is just e to the sine of x by the fundamental theorem of calculus. Okay, let's take a look at another one here. Find the derivative of h of x equal to the integral from x to 7 of sine of t dt. But now we have a problem, because the fundamental theorem of calculus here was proven for x in the upper bound of the integral. But that's okay. Just use that property to make this the negative of the integral from the 7 to x of sine of t dt. And now we can apply the derivative to that. So h prime of x is negative sine of x. All right, how about another one? Now here we have something particularly tricky, because in my bound I don't just have x, I have x squared. So that's a chain rule, right? That's a function inside of my variable position. So I need to rewrite this. I'm going to rewrite this as the integral from 2 to u of the square root of r squared plus 2r dr. And then I can say that my derivative of f with respect to x is df du times du dx. And so df du, that's the derivative of this integral, where u is my upper bound. So that's the square root of u squared plus 2u. That's the fundamental theorem of calculus. Now du dx, my u is x squared, so my derivative is just 2x. And finally, I'll just plug my u equal to x squared back in, and I get x to the 4th plus 2x squared in the square root times 2x out of it. So nothing particularly crazy here. As long as you do this substitution first and apply the chain rule, it's pretty straightforward. All right, now let's take a look at another one. So this one's even trickier, because now we have two functions of x in the upper and lower bounds. So we really got to do a little bit of manipulation here. So I'm going to start by splitting this integral at 0. You could split it anywhere really, but I'm just choosing to split it at 0. But once I split the integral up, I have the bounds in the wrong position. I need my variable up here. So I'm going to swap that around using that same property where I can make the integral negative. This becomes minus the integral from 0 to e to the x, 1 plus t cubed squared dt. So when I go to take this derivative, I need to apply the chain rule to each of these. So I'm going to rewrite this one as the integral from 0 to u. Of course, u is my sine of x, minus, and we'll call this the integral from 0 to v. And so I'll apply my chain rule to each of these derivatives. So here I get 1 plus t cubed squared. That should be 1 plus u cubed squared, right? Substitute the bound variable in, times the derivative of u with respect to x, plus, minus, and here we get 1 plus v cubed, I did it again, v cubed squared times the derivative of v with respect to x. And now we'll substitute u back in. That's going to be 1 plus sine cubed of x all squared times the derivative of sine, which is cosine, minus 1 plus e to the x cubed squared times the derivative of e to the x, which is e to the x. And there, we're done. That answer's fine. Okay, so now let's tackle another theorem. So this is just a reworking of the mean value theorem into the description of integrals. So I'm not going to reprove this. Again, all this is basically just rewriting the same exact mean value theorem, but we're doing it in the language of integrals. So if f is continuous on the interval from a to b, then there exists a number c in the integral from a to b such that f of c, the average value of f, is equal to 1 over b minus a times the integral from a to b of f of x dx. So keep in mind, right, what is this integral from a to b of f of x dx? That's cap f of b minus cap f of a over b minus a. And this is the derivative of that. So again, it's just the same statement as the mean value theorem, written with integral notation. But what that tells us is that this computation here of the integral divided by b minus a gives us the average value of the function. And that should kind of make some sense, because if we multiply this b minus a across, what do we see? The integral from a to b of f of x equals the average times b minus a. And if we look at this in a picture, that's exactly what you'd expect. You take the average value of f, right? Gives you a rectangle. That rectangle should have the same area for the average as the function area under the actual function's curve. All right, so with that out of the way, let's go ahead and tackle a little example problem. Find the average value of f of x equals x squared on the interval from 0 to 5. That's pretty straightforward. F average, that's going to be 1 over 5 minus 0 times the integral from 0 to 5 of x squared dx. That's 1/5 times x cubed over 3 evaluated from 0 to 5. That's 1/5 times 5 cubed over 3 minus 0. 1/5 times 5 cubed over 3, that's going to be 25 over 3. All right, and with that done, we'll just mention one last thing here. The net change theorem. So the definite integral of a rate of change is the net change. So this is something we've already talked about a bit. This isn't really anything new. We're just formalizing the language here that we've been using. So, for example, if I take the integral from time 1 to time 2 of the velocity, what do I get? The antiderivative velocity is position, so I get p of t2 minus p of t1. So in other words, the definite integral of velocity from t1 to t2 is the change in position from t1 to t2. In general, with any rate of change, when you take the definite integral, you're getting the net amount of that change. Now, on the other hand, if you wanted, say, total distance traveled, you would take the absolute value of the function to deal with total distance traveled, as opposed to net distance, because when we deal with the integral generally, let's say you walk 5 miles to the grocery store, and then you walk 3 miles backwards to go to the post office, and then you walk another 4 miles to go to your friend's house. So you went up 5, back 3, so now 2 plus 4, so 6, right? So your net amount of miles was 6, but what you actually experienced walking was a lot more than 6 miles, right? So if you want the total distance traveled, you've got to take the absolute value, and we can see that in this graph here. If you look at the velocity of t, you've got a positive portion and a negative portion for this graph. But when you take the absolute value, the negative part flips upwards. And so when you integrate that, it will give you the total distance traveled. All right, but we're going to go ahead and stop it there. That's going to be the end of this Calculus 1 series. So thank you for sticking out and watching everything, and have a great day.